Hey guys, welcome back to General Chemistry. This time we're going to cover Chapter 6. So Chapter 6 is going to talk about composition of substances and solutions. It's kind of a general overview if you're in my course. So we've covered actually a lot of Chapter 6 already. So formula mass we actually covered last chapter. And then really the only things we need to cover in this chapter are molarity, and then other units for solution concentrations. And then there's a big one here, titration. So titrations is going to be probably the most difficult video in this lecture series. So pretty short chapter, but let's get to it. So solutions. What we have been talking about up until this point is kind of building from the ground up. So we talked about subatomic particles, protons, neutrons, electrons. We talked about atoms. We talked about the electrons that are located around the atom. They kind of dictate how molecules form. Then we talked about molecules. So we talked about covalent, we talked about ionic, and made these compounds. And then in the last chapter, we talked about chemical reactions. So if I take two of these molecules, I put them in the same place, chemical reaction is going to take place, and then we quantified that. So what we're going to do is kind of take a little bit of a turn off of that linear path, and we're going to talk about solutions. So what happens when I take these molecules that we created and I put them into a beaker of water? So that's what we're talking about now. We still have those molecules, but we're going to do something a little bit different with them. So just as a reminder, solution, the definition is a homogeneous mixture of two or more substances. So homogeneous was a term we experienced back in chapter 1. So homogeneous or homogeneous means uniform throughout. So when I take these molecules and I put them into a beaker of water, it's still going to look uniform throughout. It's going to look the same from top to bottom. There's going to be two or more substances in there, and we're going to have names for each of those. And these will be terms that I use, so make sure that you do know them. The solvent is going to be the substance in greatest proportion. Very often in general chemistry, that's going to be water. As you get to organic chemistry and some more complex situations, that could be other things. But 95% of the time, it's going to be water for this chapter. The solute is any other substance in lesser proportion. So this could be one thing, it could be 20 things, but it's anything that is not in the majority. So kind of the poster child for an example of a solution would be like ocean water, seawater. So the solvent, of course, would be H2O, would be the water. And then the solute would be any other substance that's dissolved. So salt, fish poop, nitrogen, oxygen that's dissolved in there, so any number of things. When we talk about solutions, quite often we talk about concentration. So the concentration is going to be the relative amount of a given solution component. So if we stick with our seawater example, we could talk about the concentration of salt in the water. We could talk about the concentration of oxygen that's dissolved in the water. So it's going to be a particular solute and looking how much or how little there is in that water. Okay. This is going to lend us to two kind of different categories. So dilute is going to have a small amount of solute compared to solvent. So teeny tiny little bit of salt, whole lot of water. A concentrated solution would have a large amount of solute per solvent. So this would be like a lot of salt in the same amount of water. Another silly example that I like to use here is sweet tea in the south versus sweet tea in the north. Sweet tea in the north or anywhere else is going to be diluted. So we put a little bit of sugar in our cup of tea, and it's just slightly sweet, right? That would be a dilute solution. Sweet tea in the south, we have like a 50-50 ratio, right? So we put a whole huge scoop or two of sugar in our tea in the same glass of tea, right? So it's going to have that really strong sweet flavor. So that would be concentrated, a large amount of sugar in that same glass of tea. So that's just the definition of dilute and concentrated. Then we got to talk about the unit that we use for concentration. So we don't talk about concentration qualitatively like dilute or concentrated. We can actually give it a number. So the new unit that we will introduce in this solution series is molarity. Molarity is denoted with a capital M, so that's how we know that we're speaking of molarity. And it's defined as the number of moles of solute in exactly 1 liter of solution. Okay, so that's kind of the English definition. Here's your mathematical definition. So if we look, first over here, we've got that capital M for molarity. On the top, we're going to have to put moles of our solute. And then on the bottom, we're putting our liters of solution. So molarity is going to be moles divided by liters. Here's the formula for molarity. So molarity is denoted with a capital M. On top, we denote moles with the number N. Do not ask me why. Probably because there's a million other M's in formulas. But here's kind of a silly way that I remember this. When I see that lowercase n, my brain thinks number of moles. So that's a way to connect the N to moles. So on the top, we'll have number of moles. And then V on the bottom, V stands for volume. And that volume has to be in liters. We have to put it into liters. Okay. So let's look at a example and kind of work through a molarity problem. So if you dissolve 25.5 grams of potassium bromide in enough water to make a 1.75 liter solution, what is the molarity of that solution? What is the molarity of that solution? All right, so all right, so let's get our formula onto the paper. So our formula says we're going to solve for molarity. We're going to have number of moles on the top, volume on the bottom. So when I solve using a formula like this, I like to just take inventory of what I know and then leave out what it is that I'm trying to solve for. Okay. So first, molarity. Is there anything in this problem that tells me the molarity? Well, no. That's exactly what it's asking for. What is the molarity? So this is likely what we are solving for. Okay. I'm going to skip down to volume. So volume, is there something that tells me what the volume of this solution is? So in enough water to make a 1.75 liter solution. So that 1.75 is going to be the volume. The only thing that I need to check here is my unit has to be in liters, and it is in liters. So we're perfect there. We just have to write that down. Moles. So is there anything in the problem that says, here's the number of moles? Well, not specifically, right? What's the other number given? Well, the other number given is grams, okay? So do we know a way to get from grams to moles? Yes, of course we do, right? So we use the molecular mass of potassium bromide, and we get from grams to moles. So this is a more logical scenario. So if you're working in a lab and you're making a solution, we don't have an instrument that says, here's how many moles of potassium bromide you have. So it's not logical to start a problem with moles. But we do have scales in our lab, and we do have the ability to walk over and say, oh, here's 25.5 grams of potassium bromide. So very often these problems will start in grams because that's more realistic. Okay. So before we can plug and chug into our molarity equation, I first have to make this unit conversion from grams to moles. So making that conversion, we start with 25.5 grams of KBr. Set up our train tracks. Grams of KBr is going to go down here, and moles of KBr on the top. Okay, so we're going to get rid of grams. We're going to eventually solve for moles. Okay. All right, so to get the molar mass of the potassium bromide, I'm just going to look at my periodic table. So the molar mass for potassium is 39.098. And I'm going to add that to the molecular mass of bromine, which is 79.904. So the molar mass for potassium bromide is 119.002. So in 1 mole of the potassium bromide, there's 119.002 grams. All right, so we multiply across the top, divide by the bottom. So 25.5 times 1 divided by 119.002, and we get that that is 0.214 moles of KBr. Okay. So that's the number that I'm going to put over here into my inventory. All right. So now we've got 2 of our variables in place, one that we're trying to solve for. Now it's just a simple plug and chug to solve for molarity. So chug it out. So molarity equals, we're going to put the number of moles on top. So 214 moles. We're going to put the liters on the bottom, 1.75 liters. And then we're going to get molarity equals 0.214 divided by 1.75. And we get 0.122. Now we have to think about the units for molarity. So we could just hold on to the units that we put into our equation, so nothing canceled. So we would just bring moles per liter down. So that would be a 100% acceptable answer. So 0.122 moles per liter. That would be one way. Or we could say 0.122 and put that capital M. So that's also another valid unit for molarity. And the way that we would read this one is it's 0.122 molar. So 0.122 molar solution. So both of those mean exactly the same thing. Neither one is right or wrong, just a different way to write the units. So that's your first look at molarity. This is something we're going to use in other types of problems. So make sure you guys go out and practice a few of these problems. I hope you guys found that helpful.